Hello everyone, this is Professor Roman. Let's continue the ring theory lectures. We've been discussing polynomials, and in the last lecture I laid out the game plan, so we are ready to begin. I guess the place to start is to define the degree of a polynomial over an arbitrary ring, and it's defined as you would expect to be the largest exponent in the polynomial that occurs with a non-zero coefficient. That coefficient is known as the leading coefficient of the polynomial. And if that leading coefficient is equal to 1, we say the polynomial is monic. We're also going to set the degree of the zero polynomial to negative infinity. And in that way, the degree formula will hold for the zero polynomial. Addition and multiplication of polynomials is defined in the usual way, although the behavior will be different depending on the base ring. It's going to be different in general than it is for polynomials over a field. For example, if R is an integral domain, it's easy to see that the degree formula holds, that the degree of the product is the sum of the degrees. But for example, over Z4, we have the polynomial 1 plus 2x squared is equal to 1, and so the degree formula certainly doesn't hold here. If R is an integral domain, the units of R squared bracket x are the units of R, since no polynomial of positive degree can have an inverse in R squared bracket x. But over Z4 again, because of this, for example, we see that 1 plus 2x is in fact invertible. It is equal to its own inverse in this case. If p of x is a polynomial and if sigma is a ring map from R to S, p is a polynomial over R, then we can apply sigma to the coefficients of the polynomial. And this gives us what we'll call the induced map from R squared bracket x to S squared bracket x. Defined this way, and I'm going to use the symbol either sigma p of x or p to the sigma of x. This is a convenient notation sometimes, so we'll reserve it for this purpose. One of the most useful examples of ring homomorphisms in this context are the natural projection maps, where p here is a prime. So this is a prime ideal. So this maps R to R mod ideal generated by p, and because p is prime, the ideal is prime, and so this is also an integral domain. Okay? Assuming R is an integral domain. This is how the projection map is defined. We've talked about it before. It's a surjective ring homomorphism. And the map in this context, pi sub p, is referred to as localization, the localization map modulo p. And we'll have a very important use for this in the proof of Gauss's lemma coming up a little bit later. The first item in our game plan, I believe, was inheritance. Many of the properties that a ring may possess are inherited by the polynomial ring. Many are not also. So here are some facts. If R is an integral domain, so is R squared bracket x. If R is a unique factorization domain, so is R squared bracket x. But if R is a principal ideal domain, R squared bracket x need not be a principal ideal domain. Same for Euclidean domain. So as I mentioned in the last lecture, the weaker properties integral domain and unique factorization domain are inherited. The stronger two properties are not. Also, if f is a field, then f square bracket x is a Euclidean domain. Now, we've actually proven some of this already. I'm going to leave it for you to assemble the proofs and think about them, except for part 2, which I will prove later, that if R is a unique factorization domain, so is R square bracket x. Now let's consider polynomials over a unique factorization domain. If p of x is a polynomial over the integers, then it's often useful, as I'm sure you know, to factor out a positive greatest common divisor of the coefficients, so that the remaining coefficients are relatively prime. So here's an example. We take the GCD of these three coefficients, which is 10, factor it out, and what's left is a polynomial whose coefficients are relatively prime. Now that's easy to do over the integers, but over an arbitrary unique factorization domain, there is in general no way to single out any particular greatest common divisor of the coefficients. As we did for the integers, we singled out the positive greatest common divisor. So we're going to have to deal with the entire associate class of greatest common divisors all at once. And that motivates the following definition. Let R be a unique factorization domain. Any greatest common divisor of the coefficients of a polynomial p of x is called a content of p of x. A polynomial that has content 1 is said to be primitive. And I'm going to let C of P denote the associate class of all contents of P. So if we have a polynomial f of x looks like this, and we factor out any content, then we have a factorization of the form f of x equals, say, alpha p of x, and p of x is primitive. Using this idea, we can extend the definition of content to any polynomial over the field of fractions of a unique factorization domain, and that's a very important step. But before we get into the specifics, let's take a look at an example, because that will basically show you exactly what we're doing even in the general case of an arbitrary unique factorization domain. This is not at all difficult, but it's surprisingly difficult to explain it all in great detail. So let's again look at the integers. We have this polynomial over the field of fractions, the rationals. And this is what we do. We factor the numerator and the denominator of each coefficient and then into prime powers, and then we use negative exponents to move everything on one line. So we have 2 times 3 squared times 5 to the negative 2. And we do the same thing with each of the coefficients. Now we can factor out, if we look, say, at the prime 2, we find the smallest exponent. So this is 2 to the 1, 2 to the negative 1, 2 to the 0. So we factor out 2 to the negative 1. For 3, we have 3 squared, and 3. So we factor out 3, and so on. And then what's left looks like this. We can then, if we wish, to clean this up, revert back to fractions, and multiply these together, and we get this. The coefficients of this polynomial are relatively prime. So it is a primitive polynomial, and this number, 3 over 350, is by definition a content of f of x. So that's the process. And for an arbitrary unique factorization domain, the concept of prime element makes sense. And we can take prime factorizations and do exactly the same thing. So let's go through it in detail. Now, it's important, though, to point out that fields of fractions are very special types of fields. They're not that far removed from their underlying unique factorization domain. The construction of the field of fractions is very straightforward. This construction of content works only for unique factorization domains and their fields of fractions. It doesn't work in more general fields. So let R be a unique factorization domain with field of fractions f sub r. Then any non-zero element of f sub r can be factored into a unit times a product of prime powers where the primes are non-associates. The exponents are integers. When we're doing factorizations of unique factorization domains, the exponents were non-negative integers. We allowed 0 for convenience, but now we must allow all integer exponents. This product is unique, essentially unique, in that if A over B can be written in two ways as such a product, then M and N are equal, and after suitable reindexing, Pi is an associate of Qi. And we say nothing about the units U and V. They don't have to be related, at least not in any obvious way. And I'm going to refer to this, just as we did before, as a non-associate prime factorization of the element A over B in the field of fractions. As to proof, we had a lemma back in chapter 5 that said that A and B, since they're non-zero, I hope I said that, yes, non-zero, have non-associate prime factorizations. And we can use the same primes. So A over B is simply this. And that has this form. So that's very simple, very straightforward. The factorizations of the numerator and denominator give us the factorization of the fraction. But there is an issue that needs to be urgently addressed here. And you might consider pausing the video and thinking about that before you read on or listen on. It's necessary to show that this factorization depends only on the element A over B in the field of fractions and not individually on the choice of A and B. So for example, if we were factoring 1/2, we should get this over the rational numbers, we should get the same result as if we factor 2/4. The numerator, it's not dependent on the numerator or the denominator, it's dependent on both at the same time. And I'm going to leave this for you to justify. Actually, I made it an exercise. Okay. So there's a solution in the book if you're interested in that. Now, as far as uniqueness is concerned, suppose we do have this situation. Okay. Well, the first thing we can do is cancel like powers of associates on opposite sides. That may introduce a harmless, necessary unit factor, but as I said before, we're not concerned with U and V. in the definition of essential uniqueness. So we can cancel as many associate pairs as possible. Then we can move any factors with negative exponents to the opposite side of the equation. Excuse me, I need a little sip of tea. And once we've done that, we now have an equation involving two non-associate prime factorizations. There are no more associate pairs because we canceled all those. But these factorizations are of elements in R because we've cleared all the negative exponents by moving the factors to the other side. Since none of the primes on either side are associates, there can't be any primes because R is a unique factorization domain. In other words, we've wiped out everything in this process. So the two sides of our factorization are essentially the same. Now this theorem is important because now we can introduce the following definition, which will lead us to the definition of the content of a polynomial over a field of fractions. So let R be a unique factorization domain and let P be a prime. That means P is a prime in R. Okay. Let A be in R and let capital A be a non-empty finite subset of R. We denote the exponent of any associate of P in any prime factorization of A, the element A, by exp sub P of A. So there's something to discuss here. If you change associates, you change prime factorizations, it better give us the same exponent. That's what we just went through. So it's well defined. We denote the minimum exponent of any associate of P appearing in any prime factorization of the elements of capital A by min exp P of A. So that's the minimum of exp P of A as A ranges over the set capital A. Same thing for maximum. Now we can define the greatest common divisor in a field of fractions. Let R be a unique factorization domain. Let A be a finite non-empty subset of F sub R. Factor each element little a in the set A using the same set capital pi of non-associate base primes. That we can do because of Lemma 5.1, or an extension thereof for more than two elements. This product, where we take each prime that appears basically in any of the factorizations and we raise it to the minimum exponent of P appearing in all the elements. This product and any associate is called a greatest common divisor of A, and will denote the set of greatest common divisors by usual GCD of A. It's worth stopping and pondering this until it becomes pretty clear in your mind that we're doing the same thing we did before, but allowing negative exponents. It's the only difference. Least common multiple, we use the maximum exponent of P in the set A. And now we can define the content. Let U be a unique factorization domain. Let f of x be a polynomial over the field of fractions. any greatest common divisor of the coefficients of f is called a content of f, and the set of contents of f, again, will be denoted by c of f. A polynomial is primitive if 1 is a content of the polynomial. Notice that a primitive polynomial will be over the field of fractions will in fact have coefficients in R, the base ring. Here are some simple properties of content. Homogeneity for any polynomial f and any element of the field of fractions, the content of alpha f is alpha content of f. So you can pull an element of the field of fractions outside the content sign. Content can indicate membership in the sense that if f of x is a polynomial over the field of fractions, then it will be actually over the base ring R if and only if its content is a subset of R. And that will be the case even if a single content is contained in R, then all the contents being associates will be contained in R. In particular, f of x over the field of fractions is primitive if and only if it belongs, that implies that it belongs to R of x. So when you say f of x is primitive, you know automatically the coefficients belong to the base ring. Alpha is a content of f if and only if f equals alpha g of x, where g of x is primitive. Now, I think it would be a very useful exercise to prove these yourself. I would guess that for most of you this is new stuff. It is, as I mentioned before, not really mathematically sophisticated. It's just a pain in the neck to write it all down carefully. And the only way you're going to get comfortable with this is if you work with it. Okay. So I'm going to skip the proof here, and hopefully, if you're interested really in understanding this, that you'll do the proofs yourself. Even part 1, which looks very innocuous, to write it out carefully does require some detail. But if you think about it intuitively, you're looking, for the content, you're looking for the greatest common, or a greatest common divisor of the coefficients of alpha f. And we know from our experience with integers, that's going to be alpha times a greatest common divisor of the coefficients of f. That's, I suppose, a good place to start would be to prove that for the integers. And once you figure out how to do that, you will probably see how to do it for an arbitrary unique factorization domain. Now that we have these properties, we can prove a key result concerning primitive polynomials known as Gauss's lemma. Let R be a unique factorization domain with field of fractions f sub r. If f and g are polynomials over f sub r, then the content of their product is the product of their contents. A very pleasing result. In particular, the product of primitive polynomials is primitive. If you have two primitive polynomials, that means their coefficients are relatively prime, each of them separately. You multiply them together, that involves a lot of, cross products and a lot of interaction between coefficients of different powers of x, you wouldn't want to jump to the conclusion that the resulting product also had relatively prime coefficients because of all the intermixing of the coefficients. Gauss's lemma says it does. And here is a more or less standard proof. The first step is to prove the second statement, that the product of primitive polynomials is primitive. So suppose f and g are primitive polynomials, then they're over the base ring R. If the product is not primitive, then there's a prime that divides the product. Prime is in R, of course. Therefore, if we consider that, call the prime P, we consider pi sub P, this is the localization map that we talked about earlier. It sends an element to the coset of the ideal generated by P, represented by that element. The localization map is a ring homomorphism. So when we apply it to Fg, it's the same as pi sub P of F times pi sub P of G. But since P divides Fg, pi sub P sends Fg to 0. But because P is a prime, the ideal generated by P is prime ideal. The quotient is an integral domain. Therefore, one or the other of these has to be 0. In other words, P has to divide either F or G. But we've assumed that F and G are primitive, and that is a contradiction. So the statement that Fg is not primitive is contradicted. Fg is primitive. And for the general statement, we can write F as a content of F times F prime, where F prime is primitive. Do the same thing for G. The content of Fg is then the content of CF, CG, F prime, G prime. By part 1 of the previous result, the constants come out in front. I guess I shouldn't use the word constant. The elements of R come out in front, but we now know the product of these two primitive polynomials is primitive, so we get this, which is the product of the contents. This is a very important result. This proof is quite elegant, slick, you might say. What nags at me is that it's a little too slick. I would like to see in a different context why this works. It works, there's no problem, but something is going on here. I just get the feeling that there's another explanation that doesn't use the localization map that will maybe turn on a light bulb. So I'm going to leave that for you to think about. Gauss's lemma has some very significant consequences. Here's a corollary. R is a UFD again. Suppose that f of x can be factored into g of x times h of x, where f and g are over the base ring R, so f here and g here. But all we know about h, and g of x is primitive. All we know about h is that it has coefficients in the field of fractions. So primitive, coefficients in R because it's primitive, coefficients in f sub R. Then, in fact, this has coefficients in R as well. So if you had an integer polynomial, and this was a primitive integer polynomial, and this was a rational polynomial, this would actually have to be an integer polynomial as well. Okay. Now suppose that f of x is over the base ring R, and it has a factorization over the field of fractions, f equals g times h. You can't say one of these must be over R, but what you can say is that there's a slightly different factorization over R. And you can get that by what I'm referring to as content shifting. That's my own term. What we do is we take the content of G, call it C sub G, any content. C sub G is, if we factor it out of G, we get G naught of X. This is primitive, so it's in R. And we take the C of G and we put it over next to H. This then is a polynomial that is over F sub R. This is over R. This is primitive. Therefore, part 1 of this very corollary tells us this is in fact over R. And we have a factorization over R. So if you have, this is an example to make it very clear. If you have a factorization of an integer polynomial as a product of two rational polynomials, you can take the greatest common divisor, you can take the least common multiple of the denominators, shove it over to the first factor, shove it over to the second factor. And also you actually have to take out the greatest common divisor and shove it over to the other factor, and the first factor becomes an integer polynomial, and this, therefore, by part 1 of this, the second factor does as well. Okay? I probably didn't say that very well, but think about it, and you will see that that's what this theorem is saying, this corollary. So any factorization of an integer polynomial over the rationals can be turned into a factorization of that polynomial over the integers with what I call content shifting, shoving an integer from one polynomial to the other, okay. Or shoving a rational number from one one polynomial to the other. As to the proof of part 1, we'll take this form, this factorization, and take the content. Content of f is content of G times content of H. Content of G is the set of units, because G is primitive by assumption, times the content of H. That's equal to the content of H. So content of f equals content of H, and the content of f is contained in R, therefore, so is the content of H. So h of x is in fact a polynomial over R. As far as part 2 is concerned, we can always do content shifting. We can always factor out a GCD of G and move it over to H. That's just associativity of multiplication, or commutativity and associativity. So we can always do that. But then when we take contents, content of f is content of G naught times content of C sub G H, which again is R star content of C sub G H, which is the content of C sub G H. And since this is in R, so is this. Gauss's lemma, as I said, was actually first expressed for polynomials over the integers, and it tells us that if an integer polynomial can be factored over the rationals. It can also be factored over the integers. That's, I guess, another indication that the field of fractions doesn't buy you a whole lot more than the base ring itself. So let's look at an example. Here's a cubic. To see that this is irreducible over the rationals, we need only check that it's irreducible over the integers. But if this has a factorization, linear quadratic, non-trivial factorization over the integers, then a times c is 1. So a is either 1 or negative 1. We can always assume it's 1 by moving the sign over. Then c is also equal to 1. And so the factorization now looks like this. It follows from this that b times e is negative 1, so b is 1 or b is negative 1. But 1 and negative 1, neither one is a root of this polynomial, so b cannot be either positive or negative 1. So in trying to determine whether an integer polynomial can be factored over the rationals in a non-trivial way, we can use this result that tells us we only have to check for integer factorizations, which can be a much simpler process. Let's take a somewhat closer look at the relationship between irreducibility over R and over f sub R. We've seen as a consequence of Gauss's lemma that for a non-constant polynomial, f is irreducible over R implies it's irreducible over f sub R, because we can factor it over f sub R. If f of x is reducible over f sub R, it's also reducible over R. The converse of this is not true. And for example, over the integers, this polynomial 2x plus 4 is reducible, but it is irreducible over the rationals. And if you pause, think about this, and get a grasp on this, the rest will follow easily. What's going on is that in both universes, you can write this as 2 times the quantity x plus 2. But over the integers, 2 is irreducible. So you have a non-trivial factorization, which is why the polynomial 2x plus 4 is reducible over the integers. But over the rationals, 2 is a unit. Inverse is 1/2. So that factorization is now trivial, tells us nothing about reducibility or irreducibility. What does tell us that this is irreducible over the rationals is that it's linear. And therein lies the difference. So to try to express this as clearly as possible, I decided that a term would be useful. So R is a UFD, a non-constant polynomial h of x over R is degree-wise reducible if it can be factored into a product of polynomials of smaller degree. Simple, just a convenient term. And I just discussed why this is an important term. Now, since reducibility over a field is always degree-wise reducibility, because constants are units, non-zero constants, we can modify this to say f of x is reducible over f sub R over the field implies it's degree-wise reducible over R. Okay. This is a content shifting issue. We factor it over F sub R. Content shifting will give us a factorization over R. But the factorization over F sub R was non-trivial, which means the factors have smaller degree than F. Therefore, what we have done in this factorization over R after the content shifting, because it doesn't change degrees, is we produced a degree-wise factorization. Now we can clearly describe the relationship. F of x is irreducible over F sub R, if and only if it's degree-wise irreducible over R. We have to exclude the taking out of elements of R, non-zero elements, because they have a profound effect over R, but no effect when factoring over F sub R, as far as irreducibility is concerned. Can also say that f of x is irreducible over R if and only if f of x is both primitive and irreducible over the field of fractions. I know this is kind of coming heavy and it's a little abstract. It's a little frustrating because it's, as I said before, it really is not that deep. It's just hard to get a handle on, I think. So if you really want to absorb this, you'll probably have to listen to the video a couple of times. We now have the tools required to prove that unique factorization is inherited. So if R is a unique factorization domain, then so is R squared bracket x. The first step is to prove that R squared bracket x has the factorization property. And we can do that using induction on degree. So let f of x be a non-zero, non-unit in R squared bracket x with the degree of f equal to d. If d is equal to 0, then f of x is a constant, so it's an element of the unique factorization domain R, and it is therefore a product of irreducible elements. So let's assume that d is greater than 0, and let alpha be a content of f. Then we can factor as before, factor out alpha, and f of x equals alpha of q of x, where q of x is primitive. Now q of x is either irreducible or it's the product of two polynomials of smaller degree, each of which has an irreducible factorization by the inductive hypothesis, and therefore so does f of x. So f of x is in fact a product of irreducible elements, and R squared bracket x has the factorization property. As for uniqueness, we can establish uniqueness of irreducible factorizations by showing that every irreducible polynomial f of x is in fact prime. And that was an earlier theorem from chapter 5. So suppose that f of x divides a product, a of x, b of x. We have to show that f of x must divide one or the other of the factors. Now if f of x is a constant polynomial, say f of x equals p, p is prime, and p divides the content of this product, ab, which is the product of the contents. And so p divides the content of A, or p divides the content of B, and accordingly P will divide A of x or it will divide B of x, and that's what we're looking for. So we can assume that R of x is non-constant and irreducible over R. Then f of x is both primitive and degree-wise irreducible over R. And since f of x is irreducible over the field of fractions f sub r, it is prime in this unique factorization domain, f sub r square bracket x, because now f sub r is a field, and this is a UFD. So f of x divides one of A or B, possibly both, over f sub r, which means, let's say we can assume it divides A of x because there's a symmetry here. A of x is g of x, f of x. Now, A of x is over R, g of x is, f of x is primitive, and g of x is over the field of fractions, but we have a theorem, a corollary actually, 6.9, that says that if this is a polynomial over R, and one of these factors is primitive, then the other factor also has coefficients in R. And so this is in fact a factorization over R. And so f of x divides A of x over R, which is what we wanted to show, and so f of x is prime.